Now we're going to be talking about the impact of intermolecular forces in solubility. So first we're going to be talking about something that you guys are familiar with, which is solubility in water. So let's talk about salt, plain salt. So if you have sodium chloride and you want to dissolve it in water, so what is it you want to accomplish? This is a solid, and we want to have this. It's going to dissociate this way. This is aqueous, so aqueous, solvated, and you're going to have chloride ions, also aqueous. But this process can be visualized. This is a crystal lattice, and we can, do the energetics, the thermodynamics of this. We're going to divide the problem in one step here, which is breaking the crystal lattice, and this is going to cost me some energy. And this is going to split this into ions, sodium gas and chloride gas. And they might need to solvate those, meaning surrounding them with water molecules. This is delta H of hydration if it is in water. In general, you would say delta H of solvation. What it is like when you are, say, for example, in water, and this is sodium, then you will be having a solvation shell. And here, remember that we have, this is delta negative, this is delta positive. So you will have a shell of solvation, and you will have like all around these ions, so helping, say, disperse the charge. So that's what is going on. So all of that forming your solvation shell. For the case of chloride, this is inverse. Say that we have, this is chloride, and now this is going to be interacting, say, with the positive end here of this dipole. Positive, negative, and many more, right? So that will be the solvation shell. Delta positive, delta negative, and so on. All of that surrounding the chloride. Let's say all of that. We're going to have a sphere of solvation. This is what's going on here. So, and we also know that we can determine whether a process is of product favor by calculating the change in gift-free energy. So we know that delta G equals of, say, solvation will be equal to delta H of solvation minus T delta S, so the change in entropy of that process. But what is involved in this? So, for example, when we consider enthalpy, these are the changes when you form bonds and break bonds. So remember that some processes require an input of energy. When you break the crystal lattice, that definitely is a plus sign. So we're going to now analyze this term. So the delta H of solvation, what it involves? It involves that you will have the change in enthalpy for the crystal lattice. How do I have the out here? Okay, so we're going to say, we're going to break, I'm going to put an else, but in general, breaking interactions between solute molecules. One is a case of organic molecules. Here is a crystal. So now I also need to break interactions between molecules of the solvent. So this is your solvent, intermolecular force. And now I'm going to have the change in enthalpy of the mix. So typically I need to add energy here, so this is going to be a plus sign. This breaking intermolecular forces between the solvent itself, say water with water, that is going to have also a plus sign, so endothermic. And this term varies. So processes, when you mix, more energy is released, so compensating for that. And if this is say exothermic, then depending on the size, the overall process will be exothermic or endothermic. So that will give me the change in enthalpy of solvation. And this varies, for example, if I dissolve magnesium sulfate in water, this is exothermic. That means the overall change here is negative. Energy is released. But if I have ammonium nitrate, this is in water. This is endothermic. And these I can feel. I have a base, say a beaker with the salt, and I dissolve it in water, and I feel like it's getting cold. So it's getting the heat from my hand to dissolve. However, even though some processes may be endothermic, they can still be spontaneous or product favor, depending on this term. But of course, when you have a process that is exothermic, we have this term being favorable overall. So what do we want? We want this, for that process to occur, we want this to be negative. Meaning, we say that this is exergonic. Here we talk exothermic or endothermic. In terms of give free energy, we say exergonic, so when this is negative, or endergonic when it's positive or reaction favor. Exergonic are product favor when this is negative. Okay, so we have all those terms. Now, in regards to entropy, there are changes as well. And when there are changes in the overall entropy of solvation, where there are changes in say in the liquid is not as much, but definitely we will have some, when something is a solid, going now and separate, that we will be, say, solute, or the crystal lattice, if you like. And that will be a change in entropy also in the solvent. And here I have a term that is the entropy of the mix. And typically when you dissolve a salt into its ions and they are hydrated, the entropy increases greatly. So even though some reactions such as ammonium nitrate in water is an endothermic reaction, so in the case of ammonium nitrate being endothermic, delta H is negative. But the entropy of mix is great, so this increases big time. So overall in that equation for ammonium nitrate, this is negative, but this is very much positive with preceding that sign. We're going to have that, I'm sorry, I did say that wrong. This is endothermic. So we're going to have the exothermic. Let's do the diagram here. So this minus that, so it will be negative when it's and exothermic. So exothermic here is enthalpy, and then define that of the product minus that of the reactant. This minus that will give you this number. So being this smaller, that'll be negative. So that is what is exothermic, and the endothermic is the other way around. In the endothermic, we will have this. So this is the difference that we're looking at. So it will be positive. So overall, in ammonium nitrate, I have delta G equal, I think I need to erase something here. I have said already the two terms. So we know that we need to break interactions, solute, solute, solvent, solvent, and that there will be changes in the mix. Now, for ammonium nitrate, that delta H overall, we know that that reaction is endothermic, so we will have something here with positive sign. But the process is still spontaneous because of the entropy, the change of entropy of the mix. That there is a big increase in entropy as we dissolve. So we're going to have a negative sign we're going to have this is positive, and this right here, this right here. Overall, the process happens because this term being negative is larger than this one. And what we want is this. So a negative delta is G to be spontaneous. All right. But this is all talking about salts. And when we're saying, but essentially the process is similar in organic molecules. We'll be looking at them. What are the changes? What intermolecular forces we need to break when we analyze the solid, pull the molecules apart. Also pull the molecules apart in the solvent. And then what happens when we mix? We will be analyzing that.